Hello and welcome to this presentation related to our Applied Maths unit. In this presentation we're going to consider past paper from January 2024. This is revision week 6. Here's an overview of the paper's contents. I'm just going to outline on this slide the type of questions contained within the presentation, and with your knowledge of the previous revision week's lectures you can decide specifically which questions you want to review at your own pace. Again, with all the presentations, I've tried to labour the solutions to show all the steps within the process of these solutions to hopefully aid your ease of understanding. So questions 1, 2 and 3 we essentially worked through within this revision session. Only other questions were left for you to work through at your own pace. For question 1, the context was a roof truss. This was essentially a geometrical problem and it involved the use of basic trig, sine, cos and tan ratios, Pythagoras' theorem, and also for non-right angled triangles the cosine and sine rules. Question 2 related to an electrical context. We were given formulae for capacitors in a particular circuit. This question essentially involves the use of transposition, quite difficult transposition, from which we generate an equation that then has to be solved using the quadratic formula. In question 3 we're given a triangle, given xy coordinates for the various points, and we are asked to calculate specific coordinates of the triangle, for example mid-length, and then using the equation of a straight line y equals mx plus c, we have to generate two equations which are then solved simultaneously using matrices, 2 by 2 matrix. Question 4 requires us to understand the formulae for periodic time and frequency. Then we have to generate simultaneous equations of this format here, and we have to solve the equations. And finally we have to differentiate a product and find the turning point. Question 5 initially relates to use of complex numbers, for which the solution involves differentiation of a function, also referred to as the chain rule. Question 6, context is a tapered pipe. The main part of the question involves integration using volume of revolution, given a specific equation for the profile of the pipe which we can integrate between limits, and the final part of the question refers to the continuity principle from fluid mechanics and use of the formula A1V1 is equal to A2V2. Finally, question 7 is a thermodynamics context. We're given an equation, Q equals mc delta T. Initially we have to transpose the equation, but the latter part of the question involves solving a first order differential equation, but using a given standard form in the question. So that's an overview of the questions, and on the following slides I will just show you these solutions. I should just say there may be other solutions that you use that solve the problems, and they may be as equally as valid as the ones I'm showing. And here are the approximate start times related to the various questions contained within the presentation, should you want to directly review a specific solution. But please note all times are rounded to the nearest minute. So here's question 1. I'm going to let you read all the questions at your own pace. This is part 1, calculating the lengths BD, shown here. Solution shown on the following slide. Question 1, part 1 solution. Let you review it at your own pace. Here's question 1, part 2. Trying to find an angle in this particular case. This is the angle we're trying to find, ABD. Solution shown on the following slide. Question 1, part 2. Here's the solution. Question 1, part 3. Trying to find the distance between points A and D. Here's the line A to D we're trying to find, and the hint here would be to use either the sine or the cosine rule. Solution shown on the following slide. Question 1, part 3. Here's the solution. Question 1, part 4. To find the lengths of the vertical line BF. Again, the hint is to initially use the sine or the cosine rule, and to find angles alpha and then theta. Question 1, part 4. Here's the solution. I've used the sine rule to find angle alpha, shown here. Notice I've used the sine rule with the angle terms on the top line, In this way, that simplifies the transposition. Here's an extract from our formula sheet showing the sine rule in this format, but notice it could also be written in this format, which in this case has made the transposition slightly easier. Angle theta is found from basic trig. Solution continued on the following slide. So question 1, part 4, solution continued here. Finally calculate length BF. Use basic trig here. Here's question 2. We're given a capacitor circuit here, and we're given this formula which relates capacitors C2 and C3. Capacitor C1 is 1. For question 2, part 1, we've got to show the expression on the left hand side here, given the expression on the right hand side. So in other words, we're trying to find that C2 is equal to an expression involving C3, commencing from the given right hand equation here. But a complicating factor here in the transposition process is that C2 occurs on the top and the bottom lines of this term. So it's a fairly complicated transposition to find C2. Solution shown on the following slide. Question 2, part 1. This was the solution from the lecture, showing how we derive the formula for C2 here. This is question 2, part 1. Just my word process solution here, but same outcome. Here's our formula proved. Here's question 2, part 2. We're given this equation. So from the equation and using the result found in part 1, we're asked to show the following equation, all in terms of C3. So in other words, we're going to substitute the solution in part 1 for C2 into the equation given here to prove the equation on the bottom line. So in other words, we're given this in part 2, we've determined this equation in part 1, and we've got to show this equation. Full solution shown on the following slide. This was the in-class solution. Question 2, part 2, solution. Let you review this at your own pace. And here's the final equation. It's a quadratic equation in terms of C3. Question 2, part 3. We've got to solve the quadratic equation. Note this equation is of the form ax squared plus bx plus c equals to 0. And of course x in this case is C3. Full solution shown on the following slide. Question 2, here's the solution. Initially finding C3, ignoring the negative solution. Then we can find C2 from this formula here. C2 is 3 microfarads. Here's question 3. It's the triangle shown in the sketch. I'll let you review the solution at your own pace. Part 1. Find the coordinates of the midpoint of AB. We're going to find the x and the y values to this point here. Solution shown on the following slide. Question 3, part 1. Here's your solution. For x and the y. Question 3, part 2. Going to find the coordinates, the midpoint of BC, shown here. And question 3, part 2. Here's your solution. Question 3, part 3. It says using the coordinates of the midpoint and the vertex calculated previously. We've got to show the coordinates x, y of the centroid of the triangle. Satisfy the following equation given here. So the hint here is to use the equation y is equal to mx plus c. That's the equation of a straight line. Calculate the m for the gradient of the line, and c, of course, is the intercept with the y-axis. And here's a hint to use the midpoint of AB, coordinates 4, 7, and to use the coordinates of point C, 18, 10. Forward solution shown on the following slide. Here's question 3, part 3 solution. In this question, we're using the midpoint of line AB and the coordinates of point C. I'll let you review the solution at your own pace. Calculate the gradient m, calculate the constant c, and then rearrange for the final solution. And question 3, part 4, very similar approach. Here we're asked to derive a similar equation satisfied by the coordinates of the centroid of the triangle. Almost the same approach as for part 3. Here's a hint to use the midpoint of BC, coordinates 12, 11, and the coordinates of point A, 2, 2. Forward solution shown on the following slide. Here's question 3, part 4, solution. In this question, we're using the midpoint of line BC and the coordinates of point A. Again, I'll let you review the solution at your own pace. Calculating the gradient m, calculating the constant c, and rearranging for the final solution. Question 3, part 5. We've now got to use the matrix method to find the coordinates x, y of the centroid. So here's the equations from the previous slide. We're now going to solve using matrices. Full solution shown on the following slide. So question 3, part 5, here's the solution. Let you review the solution at your own pace. Question 4, given the displacement with respect to time graph for oscillating mass, given this formula here, including exponentials and sine functions. So question 4, part 1, got to calculate the frequency of oscillation of the mass using the graph. Solution shown on the following slide. Question 4, part 1, here's a solution. Determine the periodic time, capital T by inspection, and noting that the frequency is the reciprocal of the periodic time. Question 4, part 2, got to calculate the value of constant B in this equation. To understand how to do this, we need to realize that sine BT is the same as sine omega t, and omega is equal to 2 pi f, 2 times pi times the frequency we calculated in part 1, this value here. So that's some knowledge we need to be aware of. Once you know this, it's very easy to find the value of B. Solution shown on the following slide. Question 4, part 2, here's the solution. So the omega is 2 pi f, a standard formula. They've actually called this B in the equation here. So B, or omega, is equal to 5 pi radians per second. Question 4, part 3. So using the above formula, given now that y is equal to 120, t is 0.1, and y is equal to minus 60, when t is equal to 0.3, we've got to calculate the value of A here. So essentially we're given information from which we can generate two simultaneous equations. Solution shown on the following slide. For question 4, part 3, here's the solution. I'm going to generate two equations. Equation 1 shown here, equation 2 shown here. And in this case, we're going to divide equation 1 by equation 2. Here's our value for A. Question 4, part 3. Here's an alternative solution. This is the way I solved the problem. It's slightly more lengthy. Still generating two equations. Equation 1 here. Equation 2 here. But in this case, as both equations equal to A, I can equate equations 1 and 2. And again solve for A. Exactly the same value, of course. The first solution I've shown is probably the preferable one, but this solution might be more so familiar to students. Question 4, part 4. Got to calculate the value of A. Solution shown on the following slide. Question 4 continued. This is part 4 solution. Using equation 1 from the first method of generating the simultaneous equations. Rearranging the equation, we find the value of A, 169.7. Question 4, part 5. Calculate the time at which Y attains the maximum value, given the answer to 4 decimal places. So we're using the equation derived in part 3. We're going to have to differentiate it, equate to 0, and solve. This will involve differentiation of a product. Here's an extract from our formula sheet showing the product rule. Note, of course, that u and v are both functions of x. Here's an extract from our formula sheet showing the standard differential table. And question 4, part 5, here's the solution. Don't forget it's the product here because e is a function of t and the sine is a function of t. So it makes it a product. Product formula shown in our formula sheet. Here's the full solution. Question 5. Context here is an aircraft, given vectors for aircraft 1, aircraft 2. We've reviewed a question similar to this in a previous revision lecture. Part 1, we've got to derive a formula for the distance between the two aircraft as a function of t. Solution shown on the following slide. Question 5, part 1 solution. You review this at your own pace. Solution shown here is a vector property, displacement, whereas a scalar property here is distance. Notice the multiplying by 50 is because in the question displacements from a common origin in units of 50 kilometers. Question 5, part 2. To calculate the time at which the distance between the aircraft is a minimum, give an answer to 2 decimal places. This involves differentiation of the formula from part 1, which is a function of a function. Solution shown on the following slide. Question 5, part 2. Here's the solution. Here's the formula for distance. Note in this case the 50 can be ignored from the calculation, it will just cancel out anyway. So it's not been used in the lines below. Expanding the brackets and collecting the terms together, we find S is this bracketed term as a function of t raised to the power of a half. It's a square root here. So that makes it a function of a function. So again, we have the function of a function rule in our formula sheet. Here's an extract from our formula sheet showing differentiation of a function, sometimes referred to as the chain rule. Right, you review the solution. Time calculates to be 0.4 to 2 decimal places. That's 0.4 hours. Question 5, part 3. We've got to calculate the minimum distance in kilometers that the aircraft are apart and determine whether or not the two aircraft will remain at a safe distance to each other. So basically calculating the time in part 3 of 0.4 hours, we can now insert that into the distance equation in part 1 and calculate the value of S. Solution shown on the following slide. Question 5, part 3. Here's the solution. That's calculated to be plus or minus 10 kilometers, so the aircraft is safe. As the minimum distance required is 5 kilometers, stated in the question. This question 5, part 3, just an alternative approach. It's question 6. In this case, we're given a trig identity to use, simplifies the integral. Essentially, this is a solution involving the integration using volume of revolution. Question 6 continued. We're given the Cartesian coordinate system here. Question 6 continued. So part 1, we have to calculate the volume of this section. We're given the integral for volume here. Standard formula is pi r squared integrated with respect to x between the limits of 0 and 100. Given above, we have r as a function of x. So that's the expression we're going to integrate with respect to x. Here's an extract from our formula sheet showing the table of indefinite integrals. Solution shown on the following slide. Question 6, here's the solution. Very laboured solution here, but I hope you can follow it. So part 1, we're calculating the volume. I'll let you review the solution at your own pace. I said I've considerably laboured this solution. You don't need to show anything like these number of steps, but I'm just trying to help you hopefully understand the solution. We're now going to insert the limits on the next slide. Question 6, solution continued here. Imposing the limits now. Our final answer for volume. Answer in millimeters cubed here, and don't forget to convert to meters cubed. We divide by 1,000 cubed. Gives this answer here, or this answer here. Question 6 continued. And purely for reference, I've shown a unity bracket used here to undertake the conversion between millimeters cubed and meters cubed. There's a separate presentation related to unity brackets. Question 6, part 2. This is where we need to use the continuity equation. We're now considering speeds of flow through the vessel. We've got to calculate the speed of the water where the diameter is 40 millimeters. From the graph here, this is the 40 millimeters diameter. Given in the question the speed of flow at the 60 millimeters diameter, so we know the speed of flow through here. Solution shown on the following slide. So question 6, part 2. Here's our continuity equation. That's in general terms. For circular pipes, the continuity equation is written in this format, so we can rearrange it for V2 and calculate V2. This is an extract from our revision sheet related to fluid mechanics and the equation of continuity. So essentially this was the generic equation we were using. And finally question 7, it's actually a thermodynamics context here related to heat energy. So part 1, the heat energy Q in joules required to raise the temperature of a liquid water mass m kilograms, and specific heat capacity C by temperature delta T is given by this formula. We've seen this before in our engineering science lectures. I'll let you read the question at your own pace. This first part of the question essentially involves using the formula to find Q given the information in the question, from which we can then find the time taken knowing the power stated in the question. Full work solution shown on the following slide. So question 7 is the solution to find Q and then to find the time taken. Question 7, part 2, the final part of the question is essentially solving a differential equation. given the form here, and we're given the standard integral shown above that we need to use as part of the solution. I'll show you the full work solution on the following slide. Again, I've labelled the solution. Question 7, continued. Here's the solution. I've labelled the solution, so I've tried to include all the steps required. Obviously, you do not need to be this detailed in your solutions. I'll let you review the solution at your own pace. Solution continued on the following slide. Question 7, solution continued. Here's our final expression for t. Again, I've immensely laboured this solution. So that concludes the January 2024 paper solutions. I hope again it's been of some use to you. Hope I haven't made too many mistakes within my solutions. And as always, I wish you well with the impending examination.